Hello and welcome back to Unit 7. In this second part, we're going to introduce the concept of work. Now, work is one of those words in physics where the physics use of the word is very, very different from the everyday use of the word. So much so that I know well-respected faculty members who do not use the word work. Instead, they make it kind of German and call it Werk. Okay, well, we're not going to go there. Just acknowledge that work in physics is something very different. It is not like homework. It is not that thing you go to when you're not in class where it gives you a paycheck. It's something different. Okay. Before we jump into what exactly work is, we're going to take a little aside here and we're going to talk about units. Okay. The SI unit of work and energy is joules. By definition, 1 joule is 1 kilogram meter squared per second squared, or you might see it written as 1 Newton times a meter. There are many, many, many other other units possible for work and energy. They include calorie, both small c and large c, the kilowatt hour, BTUs, electron volts. I haven't even listed them all. Okay. So what is work in the physics sense? Okay. Work occurs when a force is applied to an object causing it to move. Okay, so now think about this for a second. If you find the biggest and heaviest book you can find, usually it's a physics textbook, but maybe it's a dictionary, and you hold it out at arm's length straight in front of you and do your best to hold it completely still. And pretty soon your arms get tired. Your hands and arms start shaking because of all you're exerting. That book is not moving. You're doing your best to hold it still, which means by the physics definition, you are doing no work. Congratulations. Okay. So what exactly is the physics definition? Okay, well, if I have a move I'm doing from, say, A to B, I can look at a little portion of this path right there, and that is going to be a length dr, or a displacement dr. And it's going to have a direction, and that direction will be pointing along the path from A to B. Okay. Then the work is the force causing whatever it is to move along that path, dotted with that little displacement piece. Work is F dot dr, or as we learned in the last part, we can write that as F dr cosine of theta. And if I want to find the total work to go from point A to point B, that is going to be the integral along the path of F dot dr. Okay. You need to be able to do a path integral to do this. For this particular unit, you will be okay not fully understanding what a path integral is. Okay. In Unit A, I will go into more depth what exactly a path integral is. Okay, so it's coming. Don't think I've forgotten about it. Okay. So now, let's simplify our lives. Okay. And let's consider a constant force. So if we go to our definition of work, which is an integral along the path, work from A to B, along the path of F dot dr, Well, then I can expand this to be the integral along the path of f of x dx plus f of y dy plus f of z dz. Okay. Now I can separate this out into three separate integrals. So I have the integral of f of x dx plus the integral of f of y dy plus the integral of f of z dz. Okay. But if the force is constant, that force pulls out of the integral in all three cases. Oh, I lost an integral sign. We'll just stick it right in there. And this is going, again, from A to B, because it's work to get from A to B. I lost an integral sign there, too. So we'll stick in our limits of integration everywhere. Okay. Well, that is going to equal f of x times the x position at A minus the x position, x position of B minus the x position at A, plus f of y multiplied by yb minus ya, plus f of z times zb minus ca. Or, in other words, f of x times delta x plus f of y times delta y plus f of z times delta z. Okay. Now, if you consider that our original force F was f of x I hat plus f of y j hat plus f of z z hat, delta r would be delta x I hat plus delta y j hat plus delta z k hat. And now consider f dot delta r. You will get exactly this bottom line here. So when we have the work due to a constant force, we can simplify our lives immensely by realizing it is the dot product between that constant force and the displacement. So now let's do a couple of examples. We have a force here, f of x. We want to know what is the work done by this force as x goes from 0 to 3. It isn't stated, but it's implied that this is the x component of the force. So my work will be the integral of f of x dx as x goes from 0 to 3. Okay, so that is the integral of 2x squared plus 4x minus 3 dx from 0 to 3. Remember, when you integrate, you take the exponent and add 1, and then divide by that new exponent. Notice for the lower limit of integration, if I plug 0 into every term, I'm going to get 0. That just leaves the answer being what happens when you plug in the upper limit of integration. 4 divided by 2 is 2, so I'm going to simplify that. And then I'm just going to put a minus 0 at the end to acknowledge that, yes, there was a second limit of integration. And if I put this all into a calculator, you find that the work in this case is 27. Now, ideally, you would have been given units. Since you weren't, we're just going to leave the answer unitless. For the next example, we are given a graph of f of x versus x, and you want to know how much work is done by this force between x equals 2 and x equals 4. So that would be here. And notice I created a box because remember that what we want is the integral of f of x dx from 2 to 4. Now we have a couple of choices. One, we could find the equation for this line and integrate it. But the other thing we can do is remember that you can take a numeric integral by finding areas, which is why I drew a box, because I'm going to subdivide this area into two pieces. I have a triangular piece and a rectangular piece. I'm going to call the rectangular piece piece 1 and this piece 2. So my total area, which will be the work, will equal A1 plus A2. The area of part 1 plus the area of region 2. 1 is a rectangle, so the area is found by length times width. The length is 2. The width is 6. So the area there is 12. A2 is a triangle, so the formula there is 1/2 base times height. So that's 1/2 times 2, and the height of the triangle is 3, which works out to be 3. So my total area, and therefore my work, equals 15. Lastly, I'm going to do an example of a person climbing a mountain. I give you the angle of the slope. Okay. And he's going to go 1 kilometer up. Okay. Now we're going to assume that this person walks up the hill at constant speed. Okay. If I consider the forces on my person as the mountain is climbed, I have a normal force. I guess I should draw you a little picture here. Here's my person on the side of the mountain. I have the normal force pointing perpendicular to the surface of the mountain. I have the gravitational force pointing downward. And I have a force of friction. And that force of friction in this case points up the slope of the mountain, because otherwise this person wouldn't be able to climb it. You have to have something to counteract gravity pulling you down. Okay. I'm going to take and define my coordinate system. Let positive x be that way, positive y be this way. I can now, as we've done many times before in this class, oh, that is not a very good triangle. I'm going to try again. Draw myself a pretty triangle. The weight is on the hypotenuse. This is the angle of the slope, so that will be the 10-degree angle that is given in the problem. Here is the y component, and here is the x component. Okay. Now, the net work is going to be the work due to that normal force, plus the work due to gravity, plus the work due to friction. Okay. We also know that the displacement up the side of the mountain will be parallel to friction and will equal 1 kilometer. If I consider the work due to the normal force, that would be the normal force from the mountain on the person, times the displacement, times the cosine of the angle between the two. But by definition, the normal force is perpendicular to the surface, so this becomes the cosine of 90, and the cosine of 90 goes to 0. So that force does no work. I'm going to think about gravity in 2 ways. One way is I'm going to think about what does the y component of gravity do. And much like the normal force, I need a couple more subscripts. The y component of gravity is also perpendicular to the displacement, so that is also 0 joules. Let's now consider the x component. So that would be the x component of gravity times delta r times the cosine of the x component of gravity points down the mountain. The displacement points up the mountain, so this is going to be a cosine of 180, which means this angle will be negative, or this work will be negative. So here I have WEP sine of 10 degrees times my delta R, which is 1 kilometer, with a negative out in front because of that cosine. And that works out to be minus 60 kilograms times 9.8 meters per second squared times the sine of 10 degrees times 1,000 meters, and that works out to be negative 102.1 joules. Okay. The last bit I have is the work due to friction. But we know that the person is walking up the mountain at constant speed. Therefore, the force of friction must equal the x component of gravity. And we see that the friction and the displacement are in the same direction. So if I write this as the frictional force times delta R, I would put a cosine of 0 degrees here. Since friction equals the x component of gravity, and delta R is the same for both, this will equal a positive 102.1 joules. And as I might have expected, if we think about the net work done, that would be the net force times delta R. Since speed is constant, net force is 0, and therefore we should expect the net work to be 0. Now, really quick, we've done a lot of effort here. And the question we were originally asked is, how much work does he do himself? Well, the work he does himself has to be to counter what gravity is doing to him. So the work he does himself is actually the positive 102.1 joules. This concludes this part.